Morning, Nana, everyone.
Good morning, sir.
Is my voice audible?
Yes, sir.
Audible.
No problem.
Sir.
Yes. Yes. Neha?
Nothing.
Previously, we completed a
Compton effect, sir.
సార్ చాలా చిన్నగా వస్తుంది సార్ వాయిస్.
Huh?
చాలా చిన్నగా వస్తుంది సార్ వాయిస్.
ఇప్పుడు కూడా అలాగే ఉందా?
Yes, sir.
ఎస్ సార్.
బాగానే ఉందన్నారు ఇందాక బడల్ వాయిస్.
అంటే వినిపిస్తుంది కానీ చాలా చిన్నగా ఉంది సార్.
సరే మాస్టర్ అయితే మారుద్దాం. సరే ఇప్పుడు ఎలా ఉంది?
Okay, sir.
Now clear means loud, sir.
Okay. Right. Okay, then I think we completed Compton effect previously. Right. Then here, good morning, Nana. Do you have any doubts in Compton effect and photoelectric effect? And identified the difference between them?
Yes, sir.
Yes, sir.
Also, you got more clarity there in between the difference between them.
Sir, one doubt, small doubt, sir.
Yes.
Sir, in Crompton effect, we wrote the formula, no, sir. H by m naught c into 1 minus cos phi. In that, sir,
Yes.
means if suppose the velocity of that electron is comparable to light, we have to replace m naught by m, sir, in this formula.
In this formula, this is m naught, Nana. M naught means rest mass of electron.
Yes, sir. But if suppose that is velocity of electron is comparable to light, should we replace or not, sir? That's my doubt.
Already we replaced that formula m there in the derivation. We replaced m with m naught by 1 minus root of 1 minus v square by c square and derived this formula.
Okay. Means no need to substitute again.
No need to substitute again. Already we replaced and we wrote this one. M naught here.
Okay, sir. Okay, sir. Okay,
Otherwise, I have to write it as h by mc. Kada?
Yes, sir.
But I am writing not h by mc. M naught c means already replaced.
Okay, sir. Okay, sir.
Right now. Any other doubts? Okay, right. Then here, now we found some support to the quantum theory. Okay. Till now we found 3 supports. Many times I told in the class they are black body radiation, number 2 photoelectric effect, number 3 Compton effect. So finally here, suppose the energy is considered as a particle according to quantum theory, of course energetic particle only. Then the question arises, why don't you consider the mass particle as energy? Okay, vice versa they are asking, right? Means their intention is then particle energy is considered as a particle, then particle can be considered as an energy. Okay, this proposal only proposed by Mr. de Broglie, that you know in your chemistry, the proposal what he proposed there. If the particle is considered as an energy, then the wavelength of that particle, for a particle he gave the wavelength, that is de Broglie's wavelength, you know, no need to go, just I am writing the formula here. The de Broglie proposed, de Broglie's hypothesis means the assumption, hypothesis is some assumption. That assumption is the wavelength of a particle, moving particle, is lambda equals to, he gave h by p. Era, do you want any derivation for this?
No, sir.
Do you know it clearly in your chemistry?
Yes, sir.
Okay, right. So I think no need to give the derivation for it. All of you know it. Wavelength of a particle is, here we write lambda equals to h by p, where p is the linear momentum. All of you know that. That implies lambda is equals to h by p is m into v. Okay, actually this is the wavelength of energy, Nana, which is h by mc. Actually we have to write for energy. But for a particle which can't travel with a speed equal to speed of light, we replace that c with v, the velocity of particle. And keep in mind, even here also, like what we found in the Compton effect, there the recoiled electron, emitted electron tries to travel with a speed comparable to the speed of light. Here also you can use that concept. What if v is comparable to the speed of light? Here we can write v is comparable to the speed of light. Then again I have to write in place of m that relativistic equation, m naught by root of 1 minus v square by c square. Again here also we use the same equation, provided v is comparable to the speed of light. Otherwise directly we use lambda is equals to h by mv only, none. Okay, no change in the equation what you learnt in your chemistry. Okay, conditions applied. And this one here, h is constant, mass is constant. So better you be ready with your calculator. Here we try to write the what the wavelength of different particles here. Okay, are you ready with your calculator, Nana?
Yes.
Yes, sir.
Quickly try to solve them without wasting the time here. First I am asking, take h is 6.625 nano, as usual. H is equals to, here I write 6.625 into 10 to the power of minus 34. And now I am writing here, number 1, in terms of velocity only, right? Or suppose if you try to convert this one in terms of energy, that is better. Why? Because most of the cases they ask in terms of energy. So change I here the equation as lambda is equals to h by linear momentum. Can I write it as root of 2 me using kinetic energy? E is equals to p square by 2m in first year.
Yes, sir.
Can I replace Nano? Yes, yes.
Yes, sir.
Why? Because from this equation, P is equal to root of 2me by taking the cross multiplication. Okay. And here, suppose that kinetic energy, if the particle acquires by doing some work against the potential difference or by accelerating potential difference, can I write it as Q into V? VQ. W is equals to VQ.
Yes, sir.
Yes, sir.
Okay. Uh, Yeah, where initial KE is equals to 0, started from rest.
Yes, sir.
Final KE is equals to whatever it got. Final KE is equals to Q into V. This is KE final. That implies lambda is equals to, I write here, h by root of 2m E kinetic energy is replaced with QV, that is into VQ here. So you are getting different equations for numericals. If they give the linear momentum, we go with the first equation. Kinetic energy, we go with second equation. Potential difference, we go with third equation. Okay. Out of the three equations, here one extra part, if the speed is comparable to the speed of light, in place of m, we have to replace the relativistic equation. Okay. And in continuation, here, if you see the third equation, H already I wrote, mass and charge depending upon the particle, it will be changed. The potential difference if they give, then how you write the wavelength as a shortcut for different particles. Okay, here we are writing the shortcuts. What are the shortcuts? Here I want lambda in terms of some constant divided by root V. By taking those constants for different particles, mass and charge will be different for different particles. That constant value we have to tell either in nanometers, that is into 10 power minus 9, or angstroms into 10 power minus 10. Okay, first one I am asking, if the electron is accelerated through some potential difference, for electron I am asking electron or its antiparticle, positron, E plus. This is positron and this is electron. Both have same quantity of charge, same mass. So for both you will get the same lambda. Lambda is equals to, will you say that constant, Nana? H is 6.625 divided by root of. The value is m 9.1 into 1.6. That value I got 1.736. How much you got? Jendra, మీకన్నా నేనే ఫాస్ట్ గా ఉన్నాను. Anyone tried?
Sir, I'm getting 1.37, sir.
37. 6.625 divided by how much you did? Oh, into 2 I missed it. Sorry. It's my mistake. Into 2 is there. You are right. Into 2. Oh,
No,
in
I
under
didn't
root
do
only, కదా?
I didn't do into 2, sir. I did 9.1 into 1.6 root of.
That 2 is also there na, in the denominator.
Yes, sir. Yes, sir. Then 0.68.
So you can. Huh?
0.68 I'm getting, sir.
I got 1.22.
1 second, sir. I'll check 1
Who
second.
is correct there? 6.625 divided by root of 2 into 9.1 into 1.6. I got 1.227.
Yes, sir. Correct, sir.
Sir, 1.2.
I got the same.
Yes, sir.
1.22.
Ah,
Whole root of
correct, na? Right. Yeah,
Correct, sir.
1.227. Now we are checking the powers. H is 10 power minus 34 divided by mass is at the root of 10 power minus 31 and charge is 10 power minus 19. Okay, this thing I think 50. 50 is 25. So 10 power minus 34 by 10 power minus 25. How much I get Nana after taking to the numerator?
9.
10 power minus 9. Exactly. So can I write this in nanometer? 10 power minus 9 I got it.
Yes, sir.
Yeah,
Yes, sir.
exactly.
1.227.
Exactly. This one in textbook, they will give 12.27 by root V angstroms. They are also correct. By root V. We found in nanometers, which is equals to 12.27 by root V in angstroms. Any mistake here, Nana?
No, sir.
No, I think it is correct. So finally, this is for electron. Okay. In the same way, suppose if they ask for proton, number 2, for proton. Okay. Proton means H plus. Here, lambda equals to by root V. Only difference is mass will be changed. Mass is how much, Nana? 1.67. I got 2.86. Is it correct?
One second, sir.
Approximately
Yes,
2.866,
sir.
8658 actually.
Yes, sir.
Is it correct?
2.8658, sir.
8658.
Yes, sir.
Approximately 866. And here powers I am checking 10 power minus 34 divided by root of 1.67 into 10 to the power minus 27. And this is 10 power minus 19. 27 means 10 power minus 23.
10 power minus 11, sir.
Yes, that's what I'm saying. This is 10 power minus 23. What happened here? Are you able to see the page, Nana?
No, sir.
No, something happened. Now?
Now clear, sir.
Yes, sir.
Right. Something happened in the middle. So this is 10 power minus 34 divided by 10 power minus 20. How much now? 23. Means into 10
Yes, sir.
power minus 11 we got. Okay. 10 power minus 11 means for proton the shortcut is 0.02866 nanometer by root V. Is it correct, Nana?
Correct, sir.
Good. 2 decimals I shifted. This is the shortcut for proton. Nanometer. Of course, angstroms, 0. That is equal to 0.2866 by root V in angstroms. Okay, this is for proton. Next, usually in exam, what they ask, one is electron, other is proton, third one is deuteron. Okay, all these are shortcuts, Nana, just. Huh?
For deuteron 2E, no, sir. Means charge.
Deuteron is 2G. Yeah. Actually, H2 plus for deuteron. H12 plus. Deuteron lambda is equals to how much? Just difference is 2e.
2.026, sir.
That one, huh?
Yes, sir. Just into 2, no, sir, in
Mass,
denominator.
correct. Mass, how much you took?
సార్
Ah,
హైడ్రోజన్ ఉండేది ఒకటే ఎలక్ట్రాన్ కదా సార్ 2 ప్లస్ వచ్చింది
ఎక్కడ
హైడ్రోజన్ కి
న్యూక్లియస్ అని చెప్పడం H12 న్యూక్లియస్, నాట్ 2 plus.
ఓకే ఓకే సార్
Okay. Here mass is 2m, charge is 1.6. 2m means 2 into 1.67.
Sir,
how much you got?
0.202 in Armstrong, sir.
I think you are right. I got, yeah, exactly. I got 0.26. Yeah, correct. 26 by root 3 into 10 power minus 11. That one what Rama Alcha told, 0.02026 into, that is nanometer by root 3, or this is equal to 0.2026 angstroms by root 3. Kenan, are these two correct?
Correct, sir.
Corrections are required, Nana? No corrections are required.
No, sir.
This is for deuteron shortcut, and then one more we require, that is helium nucleus, Nana. And that's all we require, these 4 things. So we are going to for alpha particle. Alpha particle means helium nucleus. He24, not 4 plus, Nana, plus helium nucleus here. Okay. So helium nucleus means what I have to take, lambda equals to something by root 3. Charge is 2e, q is equals to 2e, mass is equals to 4m. So one more 4 I have to add here.
1.01, sir. 1.013.
1.01. Yeah, exactly. You are right. 1.013. Right. 133 we can write. 133. 132. 132. Yes. M value I took here now, mass 4m. M means mass of proton. 4 into 1.67 into 10 to the power minus 27 kg. Okay. Mass is 4. Atomic number 4. Mass number 4. So 4m. Charge number is 2. So 2e. E is 1.6 into 10 to the power minus 19. Right? Good. This is mass, and I think 10 to the power minus 27 means I will get 10 power minus 11 only again. Am I right, Nana?
Yes, sir. Yes, sir.
That implies lambda is equals to, I am getting 0.01013 by root v in nanometer, and that is equals to 0.1013 by root v in angstroms. These two values, any one value you have to remember, either in angstroms or nanometer. That's all. Okay, if you remember these values, Nana, in exam it will save the time. Okay, that's why I gave you
approximation తీసేస్తా
ఎక్కడ నాన్న approximation ఎక్కడ చేసాను?
0.0226 కి 0.02 అనుకోరా, అట్లా కొన్ని డెసిమల్స్ తీసేయడం వల్ల
అనుకోవచ్చు, తప్పేం లేదు. అంటే ఏం లేదు, అన్ని 4 digits తో చెప్తున్నాను, అంతమించి ఏం లేదు.
అదే సార్.
ఇక్కడ కూడాను ఎవ్రీథింగ్ 1 2 3 4 4 డిజిట్స్ చెప్తున్నాను, 4 డెసిమల్. ఓకేనా? Right. Then here, this is your what de Broglie's hypothesis. Really, is it only hypothesis or there any proof? You can ask. Why? Because de Broglie proposed that particle also can be considered as a mass. Sorry, as an energy. Okay. Particle ki wavelength ante usually we try to love. Sir, particle ki wavelength sense, sir, wavelength usually we give for energy, not for the particle. Here you said the wavelength for particle, sir. Is it actually correct? Okay. Same question మనకే కదా, అందరికి సైంటిస్ట్ లో కూడా వచ్చింది సేమ్ డౌట్. దట్స్ వై దే ఆస్క్డ్ ఏంటంటే డి బ్రోగ్లీస్ గారు, వాట్ ఈస్ దిస్ నాన్ సెన్స్? For energy we say the wavelength, particle usually we say mass, not the wavelength.
Sir,
For the
there is one
particle wavelength,
statement. Means in de
yes,
Broglie, there is one statement. No, sir, it is only applicable for fast-moving bodies.
not fast moving bodies, for the bodies which are not at rest.
Means we're moving with very high speed. No, sir.
బాడీస్ ఆఫ్ లెస్ సైజ్ కూడా అన్నారు, అదే చాలా చిన్న సైజ్.
చిన్న size ki you can give more speed. If the particle has more mass, you can't give more velocity, na? అందుకని యూజువలీ వాళ్ళు హియర్ వాట్ ఆర్యన్ సెడ్, actually they thought that this is applicable only for tiny particles and which are moving with a velocity comparable to the speed of light. Okay, కానీ అది కరెక్ట్ కాదు నాన్న, మిస్టర్ ఆర్యన్.
Why, sir?
Okay, later scientists, they got the Nobel Prize also for that. They conducted an experiment related to finding out the wavelength of the mass particle. Okay, and
Okay.
here here they found the wavelength practical also. Okay, of course that experiment actually they removed from our syllabus, just they give the name only for it. Okay,
Okay, sir.
so here we ask the question here, who conducted this experiment? Okay, means who found the wavelength of this particle, lighter particles, like they actually did the experiment on electron. Okay, so who found the wavelength of electron? Okay, anyone knows the name, Nana, in our chemistry?
Rutherford, sir.
ఎవరికి ఐడియా లేదా? కాదు కాదు కాదు, డావిసన్ అండ్ జర్మర్.
Okay.
Davison and German. Okay, that's why it is called as Davison and German experiment. Okay, but it is out of syllabus. That's why we are not discussing about this Davison and German experiment. They found, Nana. So here we are saying that Davison and German found the wavelength of electron, okay, at different PDs, potential differences. Okay, by accelerating the electron by using the shortcut or by using the original formula, h by root of 2mvq. Suppose by accelerating your cyclotron, I think you know that cyclotron, moving charges and magnetism లో వస్తుంది కదా నాన్న, the apparatus used to accelerate the charged particles. ఐడియా ఉంది కదా cyclotron?
No, sir.
మీరు ఇట్లా మాట్లాడితే ఎట్లరా? The device used to accelerate the charged particles. వెళ్ళలేదా ఈ పేరు ఇప్పుడు?
No, sir.
No, sir.
సచిన్ కొంచెం తెలుసు అట దాని పేరు మరి.
సరే అంటే బుక్ లో ఆ పేరు చూసాం.
సరే వదిలేసాను, నా సంబంధం లేని విషయం ఇది. ఓకే, లైక్ లీవ్ ఇట్. Then here that cyclotron used to accelerate the electrons, not only electrons, charged particles, only charged particles, not the particles like a neutron. Okay, chargeless particles, charged particles. So here using that cyclotron, suppose if they get the velocity comparable to the speed of light, again we have to change the equation according to m naught by root of 1 minus c square by c square here. And theoretically they found one wavelength here, and practically they found the wavelength using their experimentally at different potentials, and both are perfectly matching up to 4 decimals. And here now we have to accept that the wavelength is there for moving particles or not. ఇప్పుడు తప్పదు మనకి, we have to accept.
పార్టికల్ వేవ్ మోషన్ లో ట్రావెల్ చేస్తా, లీనియర్ గా కాకుండా.
అది లేదు, పార్టికల్ ఇలాగే మూవ్ అవుతుంది.
మరి ఇంక వేవ్ లెంత్ అంటే డెఫినేషన్ ఏంటి సార్ దానికి? ఒక పార్టికల్ కి వేవ్ లెంత్ అంటే
అంటే ఏం లేదు నాన్న, పార్టికల్ కి యూజువల్లీ మనం అందరం యాక్సెప్ట్ చెయ్యనటువంటి కాన్సెప్ట్ ఏంటంటే పార్టికల్ హ్యాస్ ద మాస్. యూజువల్ వి కన్సిడర్, ఇలా చెబితే ఎవరికి ఏం డౌట్ ఉండదు. బట్ పార్టికల్ హ్యాస్ ఎనర్జీ, ఓకే, విచ్ ఈస్ ఇన్ ద ఫార్మ్ ఆఫ్ కైనెటిక్ ఎనర్జీ. ఇలా చెప్పినా ఎవరికి ఏం డౌట్ ఉండదు, దే యాక్సెప్ట్. మైండ్ సెట్ అలా ఉంటుంది. బట్ ఇట్ హ్యాస్ సమ్ ఎనర్జీ విచ్ ఈస్ ఈక్వల్స్ టు hc by lambda అనగానే ఒకసారి అలర్ట్ అవుతాడు. సార్ ఇదేంటి hc by lambda you wrote there, lambda is the wavelength for the mass particle, wavelength ends are nonsense usually we ask. దీనికి భయపడే ఆయన హైపోథెసిస్ అని ఫస్ట్ పేరు పెట్టాడు. ఆయనకు వచ్చిన డ్రీమ్ ఇది, వచ్చే డ్రీమ్లో వచ్చింది, ఆయన ఒక హైపోథెసిస్ చేశాడు. వెంటనే అడిగారు, మనం అడిగినట్టే, సార్ వేవ్ లెంగ్త్ ఏంటి సార్, వాట్ ఈస్ దిస్ నాన్ సెన్స్. దెన్ పాపం నాట్ ఏబుల్ టు ప్రూవ్, he failed there to prove that wavelength is equals to h by mv. He did many experiments but not successfully completed those experiments. అది అలా వదిలేస్తాడు, డ్రీమ్ గానే ఉండిపోయింది. దట్స్ వై ఇనిషియల్లీ వి కాల్ ఇట్ యాజ్ హైపోథెసిస్. ఇక లేటర్ వచ్చే సైంటిస్టులు ఊరుకోరుగా. ఓకే, దెన్ ఆబ్వియస్ ఆర్కియాలజీ డిపార్ట్మెంట్ నుంచి వచ్చి అన్ని బయటకు దొవుతారు. ఓకే, సో హియర్ ఇదేదో వదిలేశాడు ఇక్కడ డి బ్రోగ్లీ అని చెప్పి వీళ్ళిద్దరు పట్టుకున్నారు, డావిసన్ అండ్ జర్మన్. దే కండక్టెడ్ సమ్ ఎక్స్పెరిమెంట్. ఈ ఎక్స్పెరిమెంట్స్ లో సపోజ్ ఇఫ్ ఇట్ బిహేవ్స్ యాజ్ అన్ ఎనర్జీ, then you will get some wavelengths on the smoked glass plate. ఇది ఎక్స్పెరిమెంట్ చేసేటప్పుడు ఇలా ఉంటాయి నాన్న. ఏదైనా లైట్ యొక్క వేవ్ లెంత్ క్యాలిక్యులేట్ చేయాలంటే స్మోక్డ్ గ్లాస్ ప్లేట్ తీసుకుంటారు, దాని మీద ఒక లైన్ అనేది ఆల్రెడీ దే గివ్ సమ్ స్కేల్ ఆన్ దట్, దాని మీద ఒక స్కేల్ ఇస్తారు వాళ్ళు. ఓకే, ఆ స్కేల్ మీద ఫర్ ఎగ్జాంపుల్ వేర్ ద స్మోక్ వాజ్ రిలీజ్డ్ అంటే ఒక లైన్ లాగా కనబడుతుంది మనకి. ఓకే, that line if you get at one particular line, దాన్ని బేస్ చేసుకుని we calculate the wavelength. ఇది ఎక్స్పెరిమెంటల్ ప్రాసెస్. ఓకే, అలా ఎలక్ట్రాన్ ని యాక్సలరేట్ చేసి, ఓకే, దే సెండ్ అండ్ ట్రై టు క్యాలిక్యులేట్ లైక్ హౌ దే క్యాలిక్యులేటెడ్ ద వేవ్ లెంగ్త్ ఆఫ్ ఎనర్జీ. ఎనర్జీకి ఎలా వేవ్ లెంగ్త్ క్యాలిక్యులేట్ చేస్తారో యూజింగ్ ద స్మోక్డ్ గ్లాస్ ప్లేట్, అలాగే వీళ్ళు దే ట్రై టు క్యాలిక్యులేట్ ద వేవ్ లెంగ్త్ ఆఫ్ పార్టికల్. వాళ్ళకి స్మోక్డ్ గ్లాస్ ప్లేట్ మీద లైన్ వచ్చింది, అంటే దే ఫౌండ్ ద వేవ్ లెంగ్త్ ఆఫ్ ఎలక్ట్రాన్. అంటే మూవింగ్ ఎలక్ట్రాన్ ఈస్ బిహేవింగ్ లైక్ అన్ ఎనర్జీ. ఎనర్జీ అంటే ఇట్లా మూవ్ అవుతుందని కాదురా బడుద్దాయి. దిస్ ఈస్ ద ఫార్మేషన్ ఆఫ్ ద వేవ్. అది ఎనర్జీ ఎప్పుడు కూడాను ఇలాగే మూవ్ అవుతుంది. అందుకని వేవ్స్ లో ఏం చెబుతాం, దిస్ ఈస్ ద వేవ్ నేచర్. ఓకే, వేర్ యాజ్ ద ఎనర్జీ ప్రాపగేట్స్ like this. This is the direction of propagation of energy. This is the propagation of wave.
అండర్స్టూడ్
అంతేనా? అంతేగాని ఎనర్జీ ఇలా ఇలా డాన్స్ వేసుకుంటూ వెళ్ళదు. ఓకేనా?
అర్థమైంది సార్.
రైట్ రైట్ రైట్. ఎనర్జీ ఎప్పుడు ఇలాగే వెళ్ళిపోతుంది. రైట్,
Sir,
ఇది వాళ్ళు చేసిన. ఎస్
sir, means de Broglie proposed that for every like fast means whose velocity is comparable to light, it is they will have some wavelength, sir.
no, not like that. He gave that for any particle there will be some wavelength, but the velocity should not be zero. What he said. Why?
Okay,
Because
okay.
according to his concept, he is getting lambda approaches to
Infinity.
infinity. Na?
Yes, sir.
That's why he said velocity should not be equal to zero. This is actually a beautiful theory, Nana. If you go deep into the concept, okay, కానీ అది మనం డిస్కస్ చేస్తే బోరింగ్ గా ఉంటుంది, కానీ చాలా బాగుంటుంది కాన్సెప్ట్ యాక్చువల్.
Okay,
Okay,
okay, sir.
which gives a strong support to our Vedas also.
Okay, okay.
Astrology, and it gives a strong support and give the, actually we should feel very proud by seeing this concept and what the astrology developed, how, what basis the astrology was developed.
Okay, okay, sir.
Without any science they developed the astrology, na? But science
Yes,
supports
sir.
the astrology.
Okay, sir.
This is a beautiful theory actually.
Okay, sir.
ఓకే, అది కాస్త డెప్త్ బోరింగ్ గా ఉంటుంది కాబట్టి వద్దులే మనకు అది. దిస్ ఈస్ ద స్టోరీ, నాన్న. ఓకే, దట్స్ ఇట్. సో వన్ బిట్సాట్ క్వశ్చన్ ఆల్సో ఐ గేవ్ హియర్. ప్రీవియస్లీ హీ ఆస్క్డ్ ఇన్ బిట్సాట్. ఇది మనకి మ్యాచ్ ద ఫాలోయింగ్ లో కూడా తగులుతుంది, నాన్న. ఓకే, లిస్ట్ 1, లిస్ట్ 2. వన్ సైడ్ సైంటిస్ట్ నేమ్స్, సెకండ్ సైడ్ దే గివ్ లైక్ PQRS. They give the experiments what they conducted. Okay, suppose here they give Davison and Germer. Even in MSET also he gave this list, Nana. List type lo ichadu vaadu. List 1, list 2, like match the following. Davison and Germer. ఇది దేనికి లింక్ అవ్వాలి, నాన్న?
Wavelength of
Wave
electron.
nature of
Wavelength of electron.
wave nature of particle. Suppose given like this, 1 matches to yes. Okay, second to suppose here like Hertz, scientist name, what he found, photoelectric effect. Correct, na?
yes sir.
Einstein explained, na, found మాత్రం హెడ్స్, అది మర్చిపోకూడదు మీరు ఎప్పుడు కూడా. Hertz
Okay, sir.
found photoelectric effect. So 2pp. Atla in match the following you can find many things here. Okay, akkada kuda this type of question you can find. Davison and Germer name. Okay, so this is one concept related to what the wave nature of particle. Okay, ante wave sometimes behaves as particle. Particle sometimes behaves as wave. Okay, ante the wave behaves as a particle and particle behaves as a wave. This is called dual nature. దీన్నే మనం డ్యూయల్ నేచర్ అంటున్నాం. Okay, this is the final conclusion of this chapter. So previously the experiments what we conducted, photoelectric effect, Compton effect, there we proved energy behaves as a particle. Okay, finally Here from de Broglie hypothesis and Davison and Germer experiment, we found that particle behaves as an energy. Therefore, final conclusion, always in physics, nature loves symmetry. Okay, according to physics, nature is always symmetric. If you give the respect to the nature, nature gives respect to you. Okay, if you violate the rules against the nature, then nature also violates the rules. Okay, that's why we have to give the respect to the nature according to physics. So understood, Nano? ఏదో చెప్పారు సార్, ఏం అర్థమై సావాలి అంటారు.
Understood, sir.
Okay, so in future give the respect to the nature, don't violate the rules. Okay, why? Because nowadays the modern youth, what they are feeling crazy, breaking the rules. Nowadays it is the use nature. Okay, na behavior. Right, leave it. This is the story,
Okay.
Nana. Okay, leave it. Then we are going to only the concepts related to BITSAT exam. ఇప్పుడు మన మెయిన్స్ అండ్ అడ్వాన్స్ పార్ట్ ఓవర్. ఇంకా ఇక్కడ కొంత ఎక్స్ట్రా పార్ట్ ఫర్ బిట్సాట్ ఎగ్జామ్ ఉంటుంది. ఓకే, బిట్సాట్ ప్రిపేర్ అవుతున్నారా మీరు? ఆర్ యూ విల్లింగ్ టు రైట్ ద బిట్సాట్ ఎగ్జామ్? అంటే చెప్పాలి కదా, తప్పదు.
Why not, sir?
Okay, right. Thank you. So here, coming to the BITSAT part is, they ask here the experiments conducted to find the electron and the charge on electron, of course the mass of electron. This is the extra part here in BITSAT. Okay, so there, what are the extra parts, sir? First, actually here, how they found the electron and how they developed this modern theory. Okay, for that, actually here one scientist conducted some experiment here by taking one tube. This is called as a discharge tube, Nano. And here he tried to, actually what he started, electricity was developed around in 16th century, Nana, very old one. Okay, whereas this electron was found almost in 19th century, in 1930, I think. Okay, sorry for the disturbance here. Yeah. Ramaditya. Thomson later he found, Nana. First ఆయన కాదు experiment చేసింది. Okay. Here in the 19th century. So actually he started, one scientist, experiment to pass the current through insulator. Why? Because all we know, the current won't pass through the insulators. Okay, the current passes only through conductors. Why? Because insulator, by the definition itself, you can say, does not conduct the electricity. Those materials only called as insulators. Okay, so here, why they are not conducting the electric current? Why should not we pass here? He started one experiment. What the insulator he took here, sir? Some gas or air inside the two electrodes. Actually, they are not in contact. That's why the current should not pass through this gas. Okay, And here, to pass the current through that gas, he tried to apply some large potential. Yes, yes. Yes, Nana? Someone tried to say here. Okay, right. Then here, applied some large potential difference, Nana, in kilovolts. Not volts, means like not even thousands, like 15,000, 20,000, 30,000. He went up to around 30,000 volts.
సార్ బ్రేక్ డౌన్ కోసమా?
బ్రేక్ డౌన్ కోసం. ఓకే, అదేమో 3 × 10⁶ ఉంటుంది. ఐడియా ఉంది కదా అది?
Yes,
Yes,
sir.
sir.
ఎయిర్
దట్ మచ్ ఎయిర్ కి that much large potential difference no device here creates on the surface of earth. Okay, అందుకని here he failed actually to pass the current through this gas. Okay, he left that experiment, and later some other scientists tried here. If you take usually the gas at normal 1 atmosphere, many particles will exist. So he thought that those particles are here obstructing the flow of current. That's why don't we decrease the number of particles here? That's why here he took some vacuum pump, okay, and he connected here one vacuum pump. This is vacuum pump. Okay, and he tried to evacuate the gas from it. Means he is decreasing, tried to decrease the pressure inside. Actually, pressure here will be at what pressure, Nana?
180.
What? Okay, initial pressure we took there is equals to 1 atmosphere. 1 atmosphere means 760 mm of Hg. From there, pressure is decreased. Okay, ఎంత వరకు వెళ్ళాడంటే నాట్ టు 500, నాట్ టు 100, నాట్ టు 10, sorry, not to 50. He went almost up to 10 mm of Hg. And he went to very small pressure. అక్కడికి వెళ్ళాడు. Okay, by taking the separation nearly 1 to 2 meters. What the separation between the two electrodes. Okay, ఆయన ఎంత తీసుకున్నాడు సార్? ఆయన తీసుకుంది 1 meter. Okay, this is 1 meter. The separation between the two electrodes. At that 1 meter distance, which is almost equal to the length of a tube light nowadays what we are using. Okay, 1 meter, and the pressure is decreased to 10 mm. At that pressure, at that pressure, he found a crackling sound in the tube. Crackling and disturbed discharge. Disturbed discharge in the tube. Means I think he succeeded here almost. Why? Because he found some unstable discharge here. Better I write unstable here. Unstable discharge. like when the power supply is low, how the tube light appears. Like we can see some types of waves inside like this, and we can see some disturbance in the tube light, blinking. Am I right? No, no, not LED, ordinary tube light. What I'm saying. Anyone observed this one?
Yes, sir.
At
Some
Yes,
black
sir.
low
black will
voltage.
come.
Yes, sir.
Yes, yes, yes. That type of discharge he observed here in the tube. So you are finding out some light from the discharge tube means pakka something is coming out from one of the electrodes. Nowadays we know they are electrons, but that time they don't know. That's why I'm saying someone is coming out to one of the electrodes and hitting the particles here in between the path and releasing some amount of energy. That energy is released as light. That light we are seeing nowadays in the tube light also. Okay. So we have to accept that some particles are coming out of either the one connected to positive or the one connected to negative. Anyone from
Sir,
whom they are. Yes.
sir, then when pressure is high, why it won't come, sir?
He only explained previously. When pressure is high, more number of particles are there, and those particles are obstructing what they thought later. What I'm saying.
Okay, okay, sir.
Okay, some they are assuming now here what some particles are coming out of the one of the electrodes and they are hitting the existing atoms or molecules here and releasing some amount of energy. That energy is released as light. Okay, so these electrons are obstructed by more number of gas particles. Okay, gas particles they are insulators means like obstructors, Nana, for the flow. Okay, like what the disturbances we found in 2020. Okay, so here such type of due to the disturbance the electron or something particle coming out may not be reaching to the other end. That's why we are not finding out here any current if you connect 1 ammeter here. Now you understood.
Sir, if we means it won't reach the other end, no, sir. If,
It is not able to reach the other end
because of that
if the
particles.
because of those gas particle insulator particles.
Okay, okay, sir. Okay.
ఓకే అంటే అవి ఎలా ఉంటాయంటే లైక్ పబ్స్ లో స్టార్టింగ్ లో నిలబడి ఉంటారు ఎవరు వాళ్ళని బౌన్సర్ సార్ వాట్ వి కాల్
Yes, sir. Bouncer.
లైక్ దే ఆర్ ద బౌన్సర్స్ ఫర్ ద ఎలక్ట్రాన్స్
Okay, okay.
అంటే దే ఆర్ నాట్ అలౌవింగ్ టు మూవ్ టు ద అదర్ సైడ్ వై
Okay.
దట్స్ వై వీఆర్ కాలింగ్ ఇట్ యాజ్ ఇన్సులేటర్ అది నవ్ యూ అండర్స్టూడ్
Yes, sir. Okay, sir.
గుడ్ రైట్. So here we have to decrease those bouncers for the electrons. Okay, that's why we are decreasing the pressure. Right? If further, if they decrease the pressure further, actually, finally, it is the time to celebrate now. Why? Because finally we found some light from the discharge tube means surely some particles are coming from one side to the other side and conducting some current that they tested by connecting here some ammeter and they found some current here. Okay, అయిపోయింది. What they started actually here to send the current through insulator. They succeeded here. So experiment is over now. They have to stop and they have to cut the cake. కానీ వాళ్ళు కేక్ కట్ చేయాలి. ఫర్దర్ దే కంటిన్యూ ద ఎక్స్పెరిమెంట్. ఇది సైంటిస్ట్ కి ఒక ఆర్డినరీ పర్సన్ కున్న డిఫరెన్స్. ఫర్దర్ దే కంటిన్యూ ద ఎక్స్పెరిమెంట్. Continue to decrease the pressure. Okay, to what extent sir ఎంతవరకు వెళ్ళిపోయారు సార్ decrease the pressure to 0.001 millimeter, sorry, centimeter of Hg. అంటే ఎంత అవుతుందిరా 0.01 millimeter of Hg నా 0.01 millimeter of Hg. ఓకే, ఇది అకాడమీ, ఇది ఎన్సీఆర్టీ టెక్స్ట్ బుక్ లో 0.001 ఇచ్చినట్టున్నారు. ఓకే రైట్, నో ప్రాబ్లం. 0.001 మిల్లీమీటర్ ఆఫ్ హెచ్జి. ఇక ఆల్మోస్ట్ జీరో కదా నాన్న ప్రెషర్,
ఎస్
almost very less number of particles are existing there. Okay, మనకి అర్థమైపోతుంది if you understand the theory properly. Very less chances of hitting these released particles, hitting whom? The existing gas particles. Okay, at that very low pressure they found no light is emitted by the tube. ఇప్పుడు దీనికి ఐ థింక్ నో నీడ్ టు గివ్ ఎనీ ఎక్స్ప్లెనేషన్. మీకు ఏమైనా ఎక్స్ప్లెనేషన్ కావాలరా దీనికి? Do you want any explanation for this point?
Sir, means very less sir, very less obstruction is there, no sir, when it is decreased to that 0.001.
Almost, you can say that there almost there is no obstruction, almost.
So means continuously electrons will be flowing, no sir, to the other end.
Yes, just like highway.
So then, like continuously electrons is flowing means some like current is flowing, no sir, through the circuit.
Obviously current will flow here, but he said that no light is coming from the discharge tube.
Okay sir, means that flickering, no sir, means little black that I told you
Like
told
flickering and not like that, even like tube light, when you switch on you will get some light from the tube light, no?
Yes sir.
Such type of light is not coming from the tube light. Means the discharge tube appears like how when you power off this one, how the discharge tube appears, in that same manner it is now appearing.
Okay sir. Okay.
And if you switch off the tube light, how it appears?
Means no light sir, means just plain.
In the same
plain.
It's plain, and like some in the dark room it will be appear like a dark space between those.
Yes sir.
Right.
Okay sir. Okay.
Now it is appear like some dot space in between the two electrodes. Okay, ఇది BitSat question, అందుకని color is changed here. Okay, what is that BitSat question, sir? The dark space appeared between the electrodes is called Crookes dark space. Scientist name Crookes dark space. ఇది ఆల్రెడీ BitSat ఎగ్జామ్ అడిగిన క్వశ్చన్. ఓకే, ఈ డార్క్ స్పేస్ మీద అడిగాడు ఆయన, రైట్? ఇది కూడా అడగటానికి ఛాన్స్ ఉన్న క్వశ్చన్. విచ్ వన్? At what pressure no light is coming out of the electrode? Sorry, out of the discharge.
ఫస్ట్కి 10 mm ఉన్నప్పుడు కొలిజన్స్ వల్ల లైట్ వచ్చింది కదా.
Yes, collisions are occurring అంటే what does it mean?
ఎనర్జీ ఇస్ వేస్టెడ్ అన్నట్టు.
కాదు some particles are coming out అనే దాని ప్రూఫ్ అది.
Yes sir.
Some particles are coming out of either the first electrode or second electrode. Okay, who are those particles అనేది ఇప్పుడు ఇన్వెన్షన్ స్టార్ట్ అవుతుంది.
Okay.
Yes, light is not coming. That doesn't mean I think no particles are coming out of the electrodes. Previously light is coming and some particles are hitting and particles are coming out of the electrodes. Here no light. Does it mean that no particles are coming out of the electrodes?
No sir. Collision.
No sir.
దీనికి ప్రూఫ్ కావాలిగా. ఇప్పుడు నేను నో పార్టికల్స్ ఆర్ కమింగ్ అవుట్ ఆఫ్ ద ఎలక్ట్రోడ్స్ అంటాను, then you have to prove that there are some particles still coming out of the electrodes and prove చేయాలి కదా.
కరెంట్ వస్తున్నట్టు
Ammeter
చూపిస్తారు.
ఆమ్మీటర్ కరెంట్ వస్తుంది, కానీ ఆ పార్టికల్స్ ఇక్కడ నుంచి ఇక్కడ మూవ్ అవుతున్నాయని నాకు ప్రూఫ్ కావాలి కదా అంటాను.
sir, if electrons will flow, then only current will come.
You did
అర్థమైంది
not catch my point properly.
అర్థమైంది సార్ మీది.
అంటే those are really coming out of one of the electrodes here and they are particles. అవి పార్టికల్స్ ఏనా అనేది నా క్వశ్చన్.
సార్ ఒక ఎక్స్పెరిమెంట్ లో చేసినట్లు చాలా లైట్ వెయిట్ తిన్న ఏదన్నా ఫాయిల్ పెడితే అది తిరుగుతుంది కదా సార్.
అదే చేశారు వాళ్ళు అక్కడ. One small lightweight wheel they placed in between the two electrodes. Okay, that wheel started moving. Ante really by the hit of the particles or not? Yes, from which electrode they are coming also you can conclude.
From which direction?
Suppose if the wheel moves in this direction, I can say the particles are coming in this direction.
Yes, sir.
Correct, Anna?
Yes.
So single shot, two birds. Okay, sir. Rendu proof అయిపోతుంది నాకు ఇక్కడ. That's why they placed one wheel in between these two, and they found that wheel placed in between the two electrodes starts moving towards the electrode connected to the positive. ఇది ఇప్పుడు పాజిటివ్, దట్ ఈస్ నెగటివ్ కదా నాన్న.
Yes, sir.
So here they found that wheel started moving in this direction. Ante particles are coming in this direction. Okay, those particles finally coming from, according to chemistry, is it cathode or anode?
Cathode.
That's why they are called as the cathode rays. The particles, okay, moving from one electrode to the other, are called cathode rays. Okay, in the cathode rays, the tiny particles are called, ఇప్పుడు పేరు పెడుతున్నారు వాటికి, ఆర్ కాల్డ్. ఇప్పుడు నామకరణం జరుగుతుంది, నామకరణ ప్రక్రియ. ఆర్ కాల్డ్ ఎలక్ట్రాన్స్. ఇప్పుడు ఈ ఎలక్ట్రాన్స్ బయటకు వచ్చాయి. ఇక్కడ ఆబ్జెక్టివ్ పాయింట్, అందుకని మళ్ళీ కలర్ చేంజ్ చేస్తున్నాను. హూ గేవ్ ద నేమ్ ఫర్ దీస్ టైనీ పార్టికల్స్ as ఎలక్ట్రాన్? ఇది మళ్ళీ ఒక ఆబ్జెక్టివ్ పాయింట్. హీ ఈజ్ మిస్టర్ జే నాట్ థామ్సన్, స్టోనీ gave the name as electron for the tiny particle. Okay, this is one more objective point. So J.J. Stoney, ఇక్కడ మనం గుర్తుపెట్టుకోవాలి. Okay, so who is this electron? If it is having the charge, అది cathode నుంచి వస్తుంది కాబట్టి directly you can say it is having negative charge. What is the charge? What is the mass? Tomorrow we will find. Okay, Nana? అర్థమవుతుందా?
ఓకే సార్.
Bits are
అర్థమవుతుంది.
Yes, sir.
Okay, Nana. Tomorrow we will find the charge and mass of it.
సార్.
Yes.
సార్ నా ఎక్కువ నిన్న చేసాము సార్ క్వాంటమ్ ఇది కాంప్టన్ ఎఫెక్ట్. అందులో ఐన్స్టైన్ ది ఒక ఈక్వేషన్ వాడాం కదా సార్. అపారెంట్ అదే మాస్ వెలాసిటీ ఉన్నప్పుడు మాస్ వేరే వస్తుంది. దానికి ప్రూఫ్ ఉందా సార్ ఆ ఈక్వేషన్ కి?
ప్రూఫ్ ఉంది. రిలేటివిస్టిక్ థియరీలో E = mc² నుంచే వస్తుంది.
ఓకే,
E = mc² అనేది ప్రూవ్డ్ కదా ఆల్రెడీ. అది కరెక్ట్ అయితే ఇది కరెక్ట్. దాని నుంచి వస్తుంది ప్రూఫ్.
మనకుందా సార్?
ఉంది నాన్న, ప్రూఫ్ ఉంది. కావాలంటే చెప్తానులే, కానీ అది అయినా నువ్వు నెట్లో సెర్చ్ చేసినా దొరుకుతుంది
Okay.
నీకు ఆ ప్రూఫ్. ఓకేనా? రైట్. కావాలి లేదు అంటే రేపు చెప్పమంటే చెప్తాను. అందులో పెద్ద
Okay.
problem లేదు. చిన్నది ఈక్వేషన్. రైట్. సో ఏమైనా పేజెస్ కావాలన్నా స్టాప్ చేసేనా?
పేజెస్ పెట్టండి.
ఓకే, ఫస్ట్ పేజ్. సెకండ్ పేజ్. థర్డ్. అండ్ ఫోర్త్.
ఓకే సార్.
Sir, sun will not give X-rays. Yes, correct, Mr. Aditya. Sun X-rays ఇవ్వడు. Yes. Okay, Nana. Bye everyone, Nana.
Bye, sir.
Bye, sir.
Bye, Nana. Later we will discuss Mr. Ramaditya.